In the 12th question, what do we have? X cube plus x plus 1 upon x square minus 1. And yes, there comes the interesting thing. What is that? So the first thing which we wanted to check was whether the degree of numerator is less than the degree of denominator. It's not so. So we'll have to divide the numerator with the denominator using log and division. Yes, that's the approach that you can follow. So we have x cube plus x plus 1 upon x square minus 1. This x cube plus x plus 1 can be written as a factor of x square minus 1. X times x square minus 1. Let's take care of this x cube first. What do you have? Is x cube on the left hand side. You get an extra minus x on the right hand side, right? So you get extra minus x, you need a plus x. So what you do is plus 2x, and there was a plus 1 as well, right? So that's what you get, right? This is a quotient, this is a remainder when you divide with x square minus 1. Yes, so this is x square plus 1 over here, and this is x square plus, sorry, minus 1, not plus 1. X square minus 1 is over here. Yes and yes. And this further simplifies to, on dividing this by this you get x, on dividing this remaining thing, this is 2x plus 1 upon x square minus 1. Okay, and what next? So this integral is pretty simple. Yes, this is integrable. What about this remaining one? This can be handled using two approaches. One of the approaches says that you can factorize the denominator and use the concept of partial fractions. The other approach says, why worry about that? What you can do is, this is linear upon quadratic, right? And you can use idea of linear upon quadratic. Since x square minus 1, the derivative is 2x. Yes, this is already written in that particular form. So 2x can be handled separately. 2x upon x square minus 1. This is derivative upon this. It becomes dt upon t, which is log mod t. Simple. 1 upon x square minus 1 is similar to 1 upon x square minus a square. Yes, and you know the formula for that. But do you also know? Do you also see that that formula is derived by using no other concept than partial fractions, right? No other concept than partial fractions. So yes, at the end of the day, we'll be using partial fractions one way or the other. In the formula, it is already embedded, so that's also okay. What do we want to do over here? What we can do is, let's solve it using the easier approach. Why not? So I will be equal to integral of x plus 2x upon x square minus 1. This is the derivative of this, plus 1 upon x square minus 1 dx, right? This is what I'll get. And this is equal to x, the integral is x square by 2, plus this becomes 2x dx, which is derivative of nothing but x square minus 1. So this is dt by d, which becomes log of modulus x square minus 1. And what does this become? Plus 1 upon x square minus a square. The integral was 1 upon 2a log of modulus x minus a upon x plus a. That's what you'll use over here. The identity that I'm talking about is this. 1 upon 2a log modulus x minus a upon x plus a plus constant. This is what you have. So a, instead of a, you have a 1 over here. So 1 upon 2a is 1 upon 2 into 1, which is this, log of modulus, what you have is x minus a, which is x minus 1 upon x plus 1 plus constant term. That's my required answer using this direct approach. This is using this direct approach, mind you, and that's the complete solution of this question. But what about partial fractions, sir? Could we have solved using this, this question using partial fractions as well? Yes, this question could have been solved using partial fractions as well. Let me get rid of this whole thing, this formula, and then using this remaining space, I'll show you the solution using the idea of partial fractions as well. So after this stage over here, once you divide this, I'll convert this into partial fractions. So 2x plus 1 upon x square minus 1, which can be written as 2x plus 1 upon x plus 1 x minus 1. This can further be factorized into, further written as fractions a upon x plus 1 plus b upon x minus 1. And the values of a and b are important. That is something which you can find directly or indirectly, as we know. So b will be equal to, remove this, 3 upon 2 by substituting x equal to 1. And a will be equal to minus 1 upon minus 2, which is 1 upon 2, right? So you can use those ideas, or you can compare the numerators. 2x plus 1 is equal to a times x minus 1 plus b times x plus 1. And using coefficient of x 2, which is a plus b, coefficient constant term 1, which is equal to minus a plus b what do we get? B is 3 by 2 as we said initially. A is, you can see this is 1 by 2, right? So A and B have been found, yes, and we have written the complete integral as sum of partial fractions, right? So therefore I, using this alternative approach, the yellow one, what do we get? I, which is that integral, becomes equal to this, x plus this expression, which is equal to A upon x plus 1, which is 1 by 2 upon x plus 1 plus 3 by 2 upon x minus 1 dx. This is what you get, right? And the integral of x is x square by 2 plus half, this is log modulus x plus 1 plus 3 by 2 log modulus x minus 1 plus constant, and that is the required answer. Oh, you would say, so this answer looks pretty different, is it? Yes, they look different, but they are exactly same. How do you observe that? This is x square minus 1, right? So this can be done as x plus 1, x minus 1. So what I'll get is log of x plus 1 times log of x plus 1 plus log of x minus 1 is what I'll get from here. And with this, combining with this is half of log x minus 1 minus half log x plus 1. So 1 minus 1 by 2 will be 1 by 2 log x plus 1, and 1 plus 1 by 2 log of, this is 3 by 2 log of modulus x minus 1. They're exactly same, looking different, but they're exactly same. So both of these approaches are correct, and you can solve the question using any of these. That's okay, right? That's a complete solution. That's a complete solution using first method and the second method for this particular question.